Okay, so we talked yesterday about what it means to be a three-dimensional linear equation and what a three-dimensional linear system implies. Now we're going to talk about how to solve these things with technology. So what if we had one like this, for example? Okay, so how do we solve this stuff with matrices? Well, you have to put each of the equations into standard form, which means you have to write the variables just to make things simple and repeatable. We always just write the variables in alphabetical order, increasing order from left to right, and you're going to write the terms in alphabetical order. And on the other side of the equation, you always put the number, right? So the x term goes first. If we have three variables, x term first, then y term, then z term equals number. Okay, so what you should probably do is just bookmark desmos.com. I think I mentioned this to you. And this takes you to the Desmos launch page. And then up here at the top, you have your choice of math tools. So you can go graphing or scientific, which is mostly what you're going to use. But we're now going to add this matrix calculator also, right? So everybody pop up that matrix calculator, please. And we'll go through this together. Okay, give me thumbs up when you're there, when you got the matrix calculator, when you're at that site. And again, just Desmos. If you Google Desmos matrix, that would get you there too, I'm sure. Okay, everybody good? All right, so once you're here, we need to build a new matrix. So we're going to click the new matrix button. It's going to be matrix A, and we need to make it the right size. Well, we're going to need, because we've got three equations, we need three rows. So we need to bump the number of rows up to three. And we've got three variables and a constant, right? So we're always going to need one more column than rows. So we need to make this a 3x4 matrix, 3 rows by 4 columns. And then this is where I think we kind of left off yesterday. Now we're going to just add all these coefficients. You got to be careful about this though, because remember, x, the first column corresponds to the x coefficients, second column, y coefficients, and so on. So that first row is going to be 2 goes, oh, sorry, not 3. 2 goes first. We're just writing the numbers, the coefficients. 2, what comes next? 1, what comes next? -1, and what goes last? 1/4. Okay, give me thumbs on that. Does that make sense, what we're doing? And then just what I would do, the easiest way to enter these is to hit the right arrow on your keyboard. You guys have a right arrow on the Chromebooks? Yeah, just hit right arrow. And if I hit the right arrow again, it's like reading a book. Look what it does. It goes down to the next row. Okay. What should the next row be? 3, -1, everybody. 1, what's next? 1. Okay, what do I do next? Right arrow, good. 9, 3, 0. Everybody see that? How come 0? There's no z, right? If there's a missing z, that means the coefficient is 0, and then 15/4. Okay, everybody got that? So we filled it all in. Now you have to come down and hit this button down here, this enter button, to store that matrix. Okay, and there it is. All right, this is very simple. It's so easy. All you're going to do here is you're going to go down and you're going to choose the RREF button. That stands for Reduced Row Echelon Form. You're going to do RREF, and then we want to do that to matrix A that we created. So we're going to come up here and push the A button on the matrix calculator. And look what it tells us. Okay, this is significant. This really tells us a lot of information, actually. Let me take a picture of this stuff. Okay, and I can even do this. Look, what is that convert to fraction button going to do, do you suppose? Yeah, it's going to turn all those decimals into fractions, right? So let me get a picture of this guy. then we'll talk about it. So there's everything we did right there. Okay, so if we go down and look at this answer that it generated, how are we going to interpret that? I guess I should have had these lights off. Huh? It's hard to see up there. What is that first, Arson, what do you think that first row means? How would you interpret that? Yeah, what's that one telling us? One what? 1x. Okay, good. So this is telling us 1x, which is just x. 0 is what? So no y's, plus 0y plus 0z. So those go away, right? So 1x equals what? 1/4. How about that? Look what it does. It tells us the value of x, doesn't it? That first row tells us that x equals 1/4. What does the second row tell us? Y equals 1/2. 1 times y, which is just y, equals 1/2. And the third row tells us, 1z, or just z, equals 3/4. So what's that mean then? Well, it means that we have the answer, right? The ordered triple is going to be 1/4, 1/2, 3/4. How about that? Amazing, huh? That's good. So if we go up here, then let's just check our answer. So what do we choose? Well, we're going to choose option A because the solution, we do have a solution. And the solution, there's our ordered pair. Ordered triple, sorry. Okay, let's get phones and earbuds and all that stuff away, please. I want everybody to really catch this stuff. I'm going to let you work on it here in just a second. So there's one example. Let's try another one. Why don't you guys try this one real quick. Put this into your matrix calculator. I'll do the same, and we'll just compare answers, and then we'll interpret. Okay, so I'm going to go ahead and clear. Start all over. New matrix. We could have left that matrix in there if we needed to and just made another one, right? Is that what everybody got? I'll let you finish. Maybe you're not quite done yet. Okay, give me thumbs if you got the same thing I did. Does that make sense? Okay, so let's compare that to what we got last time. Now, last time, I want you to notice something about this matrix that we got. This part, the first 3 by 3 part of that matrix, that part, that's called the identity matrix. Okay, that's the matrix equivalent of the number 1. Everybody, I should be up here, please. So when you see that, when you get the first 3 columns and 3 rows, 3 by 3 square matrix, if it looks like you've got this diagonal pattern of just ones going from the top left to the bottom right and everything else is a 0, that's telling you we hit pay dirt, right? We got it. That's giving us a solution. X equals that number, Y equals that number, Z equals that number, we're done. Okay? Now, this is different, though, what we got on this second example. We didn't get that, right? Look at that. We get 1, 1, but then there's not a 1 there. Okay? So something is different about this. When things are different, when you don't get that telltale single solution look to the matrix, where you're getting all ones and everything else is a 0 in the first square part of the matrix. Over here is going to be different. Those are going to be the answers, right? Then you know, okay, this is not a single solution. This is one of the other options. This is either going to be infinitely many solutions or no solutions. Anybody want to hazard a guess which one that this is? You say infinitely many? You're right. How come?
Because they're all zero, but right.
Okay, they're all okay. That I thought you meant something else. The right one, the fact that they're all zeros, that's okay. But there is something else going on here that tells us, okay, this is definitely infinitely many. What is the bottom row telling us? Yeah, and what's that mean? What does that mean as an equation? If I look at this bottom row here, what's that saying as an equation? 0x plus 0y plus 0z, which is equal to what? 0 equals 0. That's telling us 0 equals 0. True or false? True. Yeah, look, that bottom statement, all the variables dropped out and we got a true statement, right? What has that always meant to us in every instance in the past? If the variables all cancel and we get a true statement, what has that always meant? All reals are infinitely many, right? Does that make sense? In this case, infinitely many solutions. So this is telling us that. Okay? So what do we know? If we don't get a single ordered triple, then you look at that bottom row. If it's true, it's infinitely many. Thank you. If it's false, what do you suppose the answer is going to be? No solution. Yeah. There you go. So if it is infinitely many, I don't want to get you guys too bogged down on this, but this is pretty advanced Math 3 class. Let's just take a second and talk about what this means. If there's infinitely many, what's that look like, right? Think back to the discussion we had yesterday about what this system represents. Each of those linear equations with A's and B's, with X's and Y's and Z's in them represents a plane. What were the different ways that three planes could intersect and have an infinite number of solutions? Well, they could all be the same plane, which they're not, though, right? In this case, they're not, because not all the equations lined up and were just multiples of each other. And we won't get into too much detail on that. But the other possibilities were the planes overlapped, they intersected at a joint, right? Like, look at these two planes right here intersect at this line, right? So it could be that all the planes are intersecting at a line. That still is an infinite number of solutions. What does this first equation or the first row say here? What is the equation that comes from that? 1x. Okay, so x plus 1/7 z, that's a 7, equals 0, right? Okay. How about this one here? Well, this one's telling us y minus 1/7 z equals 0, right? If I solved that first equation for x, I would get x equals negative 1/7 z, right? If I solve the second equation for y, I get y equals positive 1/7 z. So if I wrote an ordered pair out here, look how I could write this. I could write x is equal to negative 1/7 z, y equals positive 1/7 z, and z could be any real number. Look what that does then. If z is 10, Or let's make it a more convenient number. What if z is 7? If z were the number 7, then x would be negative 1/7 times 7. That would be negative 1. Y would be positive 1. So I'd get the ordered triple 117. If z were 14, we'd get negative 2, positive 2, 14. So it's going to give us an infinite collection of ordered triples. And how do you think they're going to line up? If I were to graph them in three-dimensional space, they would all line up as some line that's traveling through three-dimensional space, like a laser beam traveling through space, right? So we don't need to get into that much detail in this class, but give me a 1 to 5 on that. Does that make sense that what we're seeing here is that it's an infinite number of solutions? And we're going to be satisfied at this point with just saying infinite number of solutions. But if you go on and study this in college, there's a class called linear algebra, which is a class people would take if they're going to be engineers or physicists or mathematicians or things like that. You take linear algebra, and then you would go into more detail, and you'd kind of explore, okay, infinite number, but how? How is that infinite number of solution constrained? What does the pattern look like? Because oftentimes that pattern is what's really important. We use these things to represent physical systems a lot of times. Like, I can remember doing a lot of stuff in college. I studied physics when you'd use matrices to represent like systems of lenses, for example, in optics. And so you'd want to know if you get some kind of a solution like this, well, this is telling you something really important. This is telling you about some kind of axis along that optical system that's really important, right? So there's a strong connection to the real world with this stuff. Okay, let's look at one more. Everybody try this one real quick. I'll just work along with you here. You can just compare yours to mine if you want to check. What do you think, Ben? What's going on with this one? Any suggestions? Anybody got an idea? Trenton, what do you think? Okay. What's our thinking on that? How do we know? Somebody different, raise your hand, please, and tell me, how do we know this isn't a single solution? Arson. Okay, 0 doesn't equal 1. There you go. Exactly, right? This one does not look, if you look at this solution here, it doesn't look like our one solution look, does it? We don't get 1, 1, 1 and zeros and then numbers over here, right? So we know it's not a single solution. Look at that bottom row, and what's that telling us? That bottom row is saying 0 equals 1, which is false. And so what's that mean then? Well, it's telling us, whoops, that's what I wanted, that it's inconsistent, has no solutions, okay? So those planes never cross. There's no place where those planes ever cross and all the planes intersect in even a single point, okay? All right, so would it be a big deal to do one like this? What do you think? I mean, what's different about this one? You added a W. So now we've got a 4x4 system. This is a 4-dimensional system, right? Each one of those lines has 4 variables. But this wouldn't really be a big deal, would it? I mean, in Desmos, all you got to do is make the matrix a 4x5 instead of a 3x4, right? And it's no big deal. Okay, let's try. I want to just look at one quick example. Yeah, one quick application of this, just to show you why this might be important. Why would we need these three-dimensional systems? So everybody take a quick look up here. Just kind of click those partway closed so you can focus up. A Broadway theater has 700 seats divided into orchestra, main, and balcony seating. Orchestra seats sell for $40, main level seats for $30, and balcony seats for $20. If all the seats are sold, the gross revenue to the theater is $20,000. If all of the main and balcony seats are sold, but only half of the orchestra seats are sold, the gross revenue is $17,200. How many are there of each kind of seat? So what are our variables here? You always look at the question. We call these X, Y, and Z. What would X, Y, and Z represent? Okay, but what about them? Is it the cost or is it the amount, isn't it? The number of seats, right? Everybody get that? So it's not enough to just say each kind of seat. We got to say, what about each kind of seat? What is it that they represent about each kind of seat? The number. So X in this case equals number of orchestra seats. We'll let Y equal number of main level seats and Z equal number of balcony. Okay, so now all we have to do is come up. How many equations do we need? We need three, right? We've got three variables, so we need three equations. Well, what does that tell us right there? Okay, so how do I turn that into an equation? Yeah, the sum of all of them is 700, right? So we get one equation, x plus y plus z equals 700. Okay. What about this information? If orchestra seats sell for 40, main seats for 30, balcony seats for 20, and if all seats are sold, the revenue is 20,000. How can we turn that into an equation? Malin, what do you think? How could we use that information? Well, the fact that they're telling us that the main ones cost 40 a piece or 30 a piece, orchestra or 40 a piece, balcony 20 a piece. And if it's a sellout, if we sell all the seats, the theater makes 20 grand. Exactly, right? So the amount of money we're making from the orchestra seats is going to be $40 times X seats. The amount of money we're making from main level is $30 per ticket times Y tickets. The amount we're making from balcony is $20 a ticket times Z tickets, and that has to add up to 20,000. Okay. Now, what about the last part here? It tells us if all main level and balcony, but only half of orchestra are sold, the revenue is $17.20. How's that going to change the blue equation? We're still selling all of the orchestra, so that's hang on, is it half of the orchestra? I could. Yeah, I'd be doing this, wouldn't I? I'd be saying 40 times half of X, right? I'm only selling half of those seats. And why not just multiply the 40 times the 1/2, right? And make that a 20, okay? So that first term is just going to become 20x. The rest of it stays the same, doesn't it? Okay, good. There's our 3x3 system. We could just quickly throw that into a matrix, right? Let's do that super quick. This Desmos matrix, I mean, this is a fast process, isn't it? It's really not a big deal. Okay, so new matrix, 3x4. What's my first row going to be, everybody? 1, 1. 700. Okay, next row. Okay, next row. Okay, good. Save that. RREF of A. What do you know? Ah, come on. Okay, so yeah, what's that telling us then? That's telling us, isn't it, that the number of X, which is orchestra seats, is 140, right? The number of main level, that was Y, is 320. And the number of balcony was 240. Let's see how we did. Yep, 140, 320, 240. How about that? Give me 1 to 5. Does that all make sense? Okay, good. All right, so just a little, this is kind of an interesting thing to contemplate here. So what's this mean? If you have a 4-dimensional linear system, now this is going to blow your mind. Think about this. Let's just work our way up through the dimensionality of linear systems, right? So a 0-dimensional linear system is a point. A 1-dimensional linear system, actually, let's think about that differently. If I have a 1-dimensional linear system, a 1-by-1 linear system, what do we get back? We just get back a number, don't we? Everybody agree? Like 1-dimensional is one equation with one variable, like 2x plus 1 equals 5 or something. We just solve for x and we get a value, right? If we have a 2-dimensional linear system with x's and y's, then we're graphing intersection, or then we're graphing, what's that look like, right? Each one of those 2-dimensional equations is a line, and if they intersect, they intersect at a point, right? So a 2-dimensional linear system with x's and y's is a line. A 1-dimensional is just a point. That's it. Like if I say x equals 4, that's a 1-dimensional system. What's that mean? That just gives me a single point in space. That's all the linear equation means. 2-dimensional with x's and y's is a line. 3-dimensional with x's and y's and z's forms a plane. What does a 4-dimensional system mean, do you suppose? Each one of the 4-dimensional systems or equations represents what? The graph of a 3-dimensional linear equation was an infinite plane. Any suggestions? Well, kind of. It's an infinite volume. It's a space, like our universe, right? So the intersection of 4-dimensional linear equations would correspond to the intersection of different volumes, like different universes or something, right? What in the world could that be? That's pretty bizarre. If you try to think about what a 4-dimensional system would look like, it's impossible to do. Go ahead and click all your stuff closed. You guys are going to think this is pretty interesting, I promise you. So if we look at 3 dimensions, we've got x, we've got y, and we've got z coming out of the board, right? And it's easy for us to see that those are mutually orthogonal, right? They're perpendicular to each other. X is perpendicular to y. X is perpendicular to z, and y is perpendicular to z. A 4-dimensional orthogonal system would have to have another axis in there that's perpendicular to all the rest. Where's it go? We can't tell. To us, it makes no sense because we live in a 3-dimensional universe, and so there's no room for a fourth perpendicular vector there, right, or axis. Okay, but it makes it a little bit easier to think about if you think about this in terms of flatlanders. Okay, what are flatlanders? Well, these are, I'll tell you what, I think I've actually got one of these already someplace. Let me, if I just go forward a bit. Where's my, oh, I gotta look at this. What did I do? Here we go. Yeah, here's some flatlanders. Okay, there's some flatlanders right there. Flatlanders live in a two-dimensional universe, right? In a two-dimensional universe, they can only come up with a two-dimensional reference frame, Cartesian system, right? All they could do in flatland is this. X and Y. That's it. That's the best they could do. And they wouldn't see it from our perspective, right? It'd be a little bit weird for them, just like it's a little bit weird for us to have that other vector coming out of the board, right? They don't have room in flatland for another perpendicular dimension. Now, it seems kind of silly to us, like these flatlanders seem kind of dumb. I mean, how can they not get that? All they got to do is just come out this way. Do they even know about that direction though? No idea, right? These poor flatlanders, if you think about what their world must look like, and I know this sounds kind of dorky, but it gives you a little bit of insight into how these dimensionalities relate. How would they see each other? How would Mr. Blue see Mrs. Red over there? Yeah, flat, right? I mean, and we can't even really visualize what that would be, but like maybe think about it this way, like if you were to poke your head into flatland, you would see this little red line segment over there, kind of, right? What would you see above and below it? I guess maybe just blackness, right? And you'd have this kind of this band of flatland everywhere and this little short little red line segment. If I got closer, the segment would get bigger, right? Is that what they see? They can't see the black above and below because they don't even have that in their vocabulary. You get what I'm saying? You got to really kind of bend your mind and think about this a little bit. But do you get the point is that we could never really appreciate what the flatlanders would ever see because we can't help but see a three-dimensional universe. That's what we live in. Theirs is going to be fundamentally different in ways that we can't understand. Could we ever explain to them what we look like? I mean, like as if I were to go into flatland, they would see, they'd see four little tiny line segments, and then eventually it becomes a bigger line segment. And you get what I'm saying? If I dive through there, it's going to constantly change. We could just tell them, well, just stack those up. Stack those up, like a CAT scan or something where you get all these thin little pictures and you put them all together. And they can't do that though, right? Because they don't know how to put stuff together up, how do you, on top of, what's that mean? They don't understand that. That's not, they can't visualize that, right? Here's what's crazy about this. So Mr. Blue, he's got this idea that he really kind of wants to impress Mrs. Red over there. So he brings her a present. The present is this beautiful piece of flat jewelry that's wrapped up in this deck, this green box. Can she see what's going on in that green box? She can't. How come? You're right. How come she can't see that? Why not? Well, for one thing, because it's inside the box, right? From her, you guys think that I'm crazy, don't you? From her perspective, it's inside this closed box. She can't see inside. Can you guys see what's inside this box? How come? It's closed, right? You can't see in there. There's no way that Mrs. Red can see inside that green box. You can, though. Without ever opening the box, you can see what's inside. You could even take out what's inside the box without opening it. That's crazy. Okay, now you didn't know this, but there is a four-dimensional classroom out there, and they're looking down at us thinking, these poor little, what do they call us, space landers, 3D landers. They can't even see what's inside this box. A four-dimensional creature could look down here, if there were such a thing, could look down here and see right inside that box and take something out of the box without ever opening it up, just as easily. And that's true. By extension, there would be a way, if you were to place this three-dimensional box into a four-dimensional universe, there would be a path to get inside the box without ever opening it, right? Isn't that crazy? That's a true story, though, okay? So can we visualize this stuff? Not really, but you get a little bit of an idea. What's this doing here? If you want to look at we're going to start with a 0 cube, then a 1 cube, then a 2 cube, then a 3 cube, then a 4 cube. So a 0 cube, a zero-dimensional cube, is just a point. The thing will start over, I think. Yeah, so there's a point. That's zero-dimensional cube. Well, let's add one dimension to it. Okay, well, now that cube translates to a line segment. 2 dimensions, it becomes a square. 3 dimensions, it becomes a cube. 4 dimensions, this is kind of hokey because we can't see 4 dimensions, but the idea is it would have to somehow expand into a 4th dimension, and this tesseract is sort of interpreted as being what the shadow of a 4-dimensional object would look like, okay? It's not, you can't see what a 4-dimensional object would be, but its shadow would probably look something like that tesseract, okay? A good way to think about this is with nets, right? A net is what you get when you unfold something. So if we take a 2-dimensional object like a square, if I unfold that, the net is just a long line segment. Pretty boring, right? What if I take a cube and I unfold the cube? Do you see that it would look something like that maybe if I unfolded it, right? If I folded all that back up as a piece of paper, I could turn it into a cube, couldn't I? Okay, so there's an example of an unfolding and refolding net of a cube. We can unfold it in different ways. There's one way you could unfold it, right? Here's a different way. But each of those works, right? They both fold back up into cubes. Okay, here's one way you could unfold a hypercube. It unfolds into a dolly cross, which looks like that. That is the net of a 4-dimensional cube. How crazy is that? If you unfolded a hypercube, 4-dimensional cube, that is one thing that you definitely would get. Crazy. Isn't that crazy? How do you fold it up? Well, we can't tell. We can't see that, right? Isn't that weird, though? Okay, so here is there's a shadow, right? This is just like a projection onto a like a hologram of a shadow of a 4-dimensional cube being rotated. How about that? You can't see what a 4-dimensional cube looks like, but that's what its 3-dimensional shadow would look like as you rotated it. That kind of blowing your mind a little bit? Isn't that crazy? And here's a different type of rotation of a 4-dimensional cube. Isn't that weird? Weird stuff, huh? All right, that's probably good for today.